Here we're going to look at question 88 from the NSAA 2018 paper. In this question, we're given this diagram, which represents a pendulum bob hanging by a light inextensible string of length 50 centimetres. We're told that our bob is released from rest at this position here, x, and then the question asks us, what is the speed of our bob of mass given here through our position y? If you'd like to have a go at this question, go ahead and pause now, otherwise let's have a go at it. Now it's worth noting at this point that the mass of our bob given in the question is written as 10g, but since it's a mass, this g must mean grams rather than being the acceleration due to gravity, which would be a weight. It's just a small point, but it's something which people might trip up on in the rush of an exam. So what's the best way of going about answering this question? Well, the easiest thing to do is probably to use conservation of energy. Now, to do this, we want to find the energy at our position x and our energy at position y, and we can go ahead and equate those two. So, what's our initial energy going to be at position x? Well, we know that the bob is initially stationary, so its only energy is going to be potential energy, which is given here by mgh, where h is this height that I've labelled on our diagram here. Now what we want to do though is to find h in terms of variables which were actually given. So we know that at y, the distance from our position y straight up to the pivot our pendulum swings about is going to be the same as the length of our string, 50 centimetres. Then we can try and find this distance in here, which is going to be added onto h to give us 50 centimetres. Now to do this, we can use our triangle of 50 centimetres by 30 centimetres, and with Pythagoras we get that this distance is equal to this here. So therefore we can say that h is going to be equal to 50 centimetres, take away this distance given here. Now what we want to do is try and find out what each of these values are going to be. So the easiest way to do this is probably with standard form, but they come out to be 50 squared as being 2,500 and 30 squared as 900. Taking these away from each other, we get that our height, h, is equal to 50 centimetres, take away the square root of 1,600. Now again, converting this into standard form is probably the easiest way to go, and it will give you that this square root of 1,600 is 40 centimetres. And therefore, the height that our bob falls, h, is going to be given by 10 centimetres. Now that we know these two distances, we can go ahead and put them on our diagram and substitute in our 10 centimetres to our equation for energy. So the potential energy is going to be the mass of our bob, which is 10 grams, or 10 to the minus 2 kilograms, multiplied by our acceleration due to gravity, which is just 10 metres per second squared, multiplied by our height of 10 centimetres, or 0.1 metres. This gives a final answer of 10 to the minus 2 joules. And then since this is the energy at position x, and by conservation of energy we know that the energy at x and y is the same, then this is also going to be equal to the energy at y. So the energy at y is just going to also be 10 to the minus 2 joules. Right, now why is this value useful? Well, we can go ahead and find an expression for our energy at y. What's this going to be? Well, since there's no potential energy at this point, it's only going to be the kinetic energy of our bob at y. So this is going to be given by a half, multiplied by the mass, multiplied by the velocity of our bob squared. So, rearranging for our velocity v, we get this expression here, and then substituting in our energy at y and our mass of 10 to the minus 2 kilograms, we get this, and then our 10 to the minus 2's are just going to cancel out, giving us that the velocity of our bob at y is just the square root of 2 metres per second. This is going to correspond to answer A given in our question.